David Smith here with another Flip Classroom math video. A few tips before we get started. First, remember that you can slow down or speed up the playback if that helps you follow along. You can also pause the video at any point to perfect your notes, or if you want to try the problems before I explain them. Lastly, remember that you could turn on the captions and read my words going along the bottom of your screen. Now we're going to do a section on modeling with linear functions. So the math isn't new here, but the concept of modeling is an important one, and it also leads to a bunch of word problems. So let's take a look. Modeling, a linear model, it's a way to describe reality. So this is kind of where mathematics comes from. People noticing things about reality, wanting to describe them with mathematics. So they create models that will predict behavior and describe behavior. So here's a nice definition of a linear model. It's a linear function that describes a relationship between two variables in a real life situation. So think about that for a minute. Two variables in a real life situation. So I put up three here that I came up with. Undoubtedly, you could come up with some more. So check it out. Rate problems. These are classic rate problems. People tend to struggle with these. The kind of thing where you have a car going down a road at a speed, and then the rate problem relates the distance traveled to the time traveled. You might have income problems. This is going to relate income earned to time worked. You work more hours, you make more pay. Finally, we can take a look at pricing problems. This is going to relate the total cost to the quantity purchased. You buy more, you pay more. Now, there's an assumption in these three examples that's an important one. What might that be? Think about that for a minute. It assumes constant rates. So you need a constant rate for it to be a linear function. So remember how our linear functions don't have squares, don't have square roots. It's just x depends on y. Maybe it gets multiplied or divided, but it's a straight linear relationship. So these types of problems are linear because the rates don't change. If you're going down a road and you're trying to calculate distance as a result of time, you have to assume the same rate for that calculation to be. Okay, here's a word problem for you. This is a car rental scenario. Commonly, people fly to other cities, they don't bring their car, they've got to rent a car to get around while they're on that trip. So what we have is a table that shows the number of days that the car is rented, and then we have the total cost in euros. So this person is maybe going to Italy or France or something like that. So here's our table. First off, which is the dependent and the independent variable? Independent, we choose it. We choose how many days we rent. The dependent variable is the total cost, and that depends on how many days we rent. So we're going to call this one X and call this one Y. Okay? So, our first step, we have a data table. Do we know this is linear or not? Think about that for a minute and see if you could prove, without graphing, that this is a linear relationship. Okay, I'm wondering if you did some calculations. I'm going to have you do a calculation. Figure out the slope between 1 and 2 days for rental. Okay, I just figured out the slope between these 2 points. I did my y2 minus y1 on the top, my x2 minus x1 on the bottom, and I get 30, 25. Have we figured out, have we proven that this relationship is linear? Yes or no? The answer is no. We just know the rate of change between these 2 points. For this relationship to be linear, the rate of change has to be the same between every 2 points. So if we were in class right now, I'd go around the room and I'd assign different numbers to different folks to calculate the rates. And the truth is, you can calculate the rate between these two, or these two, or these two, or those two. No matter which two you pick, you should get the same rate of change. So do that. Pause the video and calculate an M2, a second slope, based on any 2 points in the table. So I hope that when you calculated your slope, your gradient, your rate, you got this same 30, 25. If you didn't, you want to check your work and see where you went astray. I just used the last point and the first point in my second calculation, and lo and behold, I get 30.25. So now I want you to write a function for this relationship. Okay, let's see how you did. I chose a pretty formal path. I started with the point gradient form of an equation, of a linear equation or a linear function. It's very possible that you could just know from this example that this is your function. However, if my quiz or my test tells you to show steps, you better show some steps. So let's go through this. Y minus y1 for my table is y minus 30.25 equals m, the gradient, which is also 30.25, times x minus x1, which is just 1 for 1 day's rental. I do my distributive property, move my 30.25 over, these two 30.25s cancel, and I get f of x equals 30.25x. Now this makes sense because in our example, you can see that 1 day is 30.25, 2 days, you just add 30.25 each time. It's a pretty simple function. There's no fee that gets added on regardless. It's just that simple. Let's do another word problem. This one's a little more tricky and I'm gonna not walk you through it quite as quickly. So check this out. The relationship between Fahrenheit and Celsius degrees is linear, okay? Now I'm just telling you that and we're gonna move on. But you could expect a problem to tell you that it's linear and then ask you to prove that this is true. And remember what you would do is you'd calculate the rate of change between more than just 2 points, like maybe all of the pairs you could think of, and if you got the same rate of change every time, then you would show that it's linear. I'm not going to take the time to do that because we're going to move on to the next question. Find a function that models this relationship. So remember, we find the rate of change, and then we use the point gradient form for a linear equation to find the equation in y equals mx plus b form. Okay, let's see how you did. I grabbed my slope just between the first 2 points here, and I just do my y2 minus y1 over x2 minus x1, and I get 1.8. That's my gradient. Now I'm plugging into point slope form, so I'm using the first point there. I have y minus y1, which is my 32, m, the gradient, times x minus x1, which is 0 from the table behind me. Then I just rearrange, do my multiplication, solve for y, put it in function notation. My conversion formula for that is 1.8x times 32. Here is a straightforward calculation using our function. If the temperature is 27 degrees Celsius, what is it in Fahrenheit? So go ahead, pause the video, use your function, and tell me that answer. Okay, let's see how you did. This is a straightforward plug-in. We just did f of 27, that's degrees Celsius. We put it in for x in our function, did the math, and we get 80.6 degrees Fahrenheit. So a temperature of 27 Celsius is 80.6 Fahrenheit. Now, here's a little bit of a tougher problem. The algebra is easy, but the thinking might be a leap for you. Find the temperature when Fahrenheit and Celsius are equal. Think about that. If you get a good place to start, go ahead and crunch some numbers and see what you get. All right, let's see how you did. So your first step is to realize that the temperature has to be the same. So the Celsius temperature, when you plug that in, this equation has to generate the same number as the Fahrenheit temperature. So that would be the same x. So now I can just solve that equation for x, and I move my 1.8 over by subtracting it, leaving me with 0.8x equals 32. Divide through by negative 0.8, and I get x equals minus 40. And indeed, that's true. Negative 40, shiver me timbers, is the same in Fahrenheit and Celsius. Now that you've finished watching the video, take a moment to jot down any questions you have so you can bring them to our next class and get some help. You can also watch the video again to perfect your understanding. If you enjoyed it, please click the like button down below, and if you'd like to help me grow my YouTube channel, please click subscribe.